Good afternoon, everyone, and my name is Zilin from UNSW Sydney, Australia, and it's a joint work with many brilliant collaborators who are now all over the places. So my talk is about property-based testing. So where I'm going with this talk, formal verification, and specifically, I mean interactive theorem proving and testing. They are not enemies; they are friends, and they should be used in conjunction. And they have their strengths and weaknesses. Formal verification is more rigorous. It's formal, but testing, it's easier to do. It's easier to learn, and it's quicker. And it can cover some of the cases where formal verification cannot really deal with properly. For example, the parts that you need to assume or you need to axiomatize. So specifically for this work, I want to focus on refinement proof, just that one particular form of formal verification, and property-based testing, that particular methodology of testing. We want to use these two together in the context of COGENT. So if you don't know what they mean, doesn't matter. I'm going there. So COGENT already has the refinement proof built in it. And in this work, we want to add property-based testing into the framework so that we can try to relate these two methodologies of software quality control. And also we want to get some benefits to reach an effect of 1 + 1 is greater than 2. So let's first look at property-based testing. What does it mean? Just a very quick introduction if you don't know it. So basically, it's a form of testing. It's a testing methodology which, instead of specifying input and output pairs, you specify the your tests as logical formulas. So basically, you say what kind of properties the output has to satisfy given the some preconditions of your input data, and the test driver randomly, automatically, maybe guided by some heuristics, generate a whole bunch of test data and feed them to the tests. And the test driver will search for counterexamples and report any offending inputs to the developer. So basically, the developer can use that information to diagnose. Property-based testing it was firstly popularized by by Haskell's Quick Check library in 2000. And now it's widely available too in many programming languages and theorem provers or proof assistants. And these languages some of them are functional, some of them are imperative, which is cool. So just a quick example, if we had a sorted list type as list, and we have an insertion function, insert, we want to test this insert function. So what kind of properties we can give to this function? For example, we can say if the input list is sorted, then the output list should also be sorted, right? That's one property. Another property we can say is that the length of the list should be incremented by 1. And other things we can say is about the set inclusion relationship between the old list and the new list. So basically, everything in the old list should also be in the new list, that kind of thing. There are tons of more properties that you can say about this function. And if we just run it in Haskell, it just randomly generates 100 test cases for each of them and say, OK, this one, that implementation is correct. Cool. So we've seen property-based testing. Then let's look at COGENT and refinement proof. So COGENT is a high-order polymorphic purely functional language designed for writing and formally verifying low-level systems code. Our target has been file systems and device drivers, primarily. So COGENT comes with a uniqueness type system, which is sort of like the type system in Rust, which tracks the unique references to mutable objects. So the cool thing about this uniqueness type system is that on one hand, it allows us to give the program or to the language a purely functional semantics. And also, behind the scenes, we can do destructive updates just like you do in C. So basically, it can be compiled to performance low-level imperative code. And this is just a snippet of coding code. You don't have to read it. It's just give you an idea what the language looks like. So the verification framework, or how the general workflow of the language, is that the user writes their low-level systems code in the COGENT source code and give it to the COGENT compiler. The COGENT compiler generates a shallow embedding of the COGENT source program in Isabelle whole, and also it compiles it to C. And importantly, it also generates a refinement proof saying that the compiled C code is a correct implementation of the shallow embedding of the COGENT program. So COGENT is a restricted language, so there are lots of things that it doesn't quite support, or at least initially didn't support. For example, general recursion or any sort of recursion loops. And because it's a pure language, you cannot do I/O. You have to do memory management out of it, and also basically you need to have a hatch to escape the very restrictive type system COGENT has, just like you do in Rust. You can write in unsafe Rust, right? So for that portion of code, users can write them manually in C, and we connect the manually written C code, which we refer to as the C library, and the COGENT generated part of C. COGENT generates this C refinement proof showing that the C is a correct implementation of the COGENT semantics, which is fully automatic, but some manual effort is still are still needed. For example, we need to show manually that if there's a functional specification, which is also manually written by the user in Isabelle whole, we need to manually show that the COGENT program actually implements the specification. And also that's true for the C library. That's a bit more laborious. We have to manually show that the C code actually correctly implements the specification. But this proof, because COGENT has a purely functional semantics, this refinement proof should be much easier to do because we can use equational reasoning techniques. And for the C part, because the C library is shared, that's why we call it the library, so the effort should be amortized over time. We use data refinement as a key methodology for proving the correctness of the COGENT programs. So simply speaking, for each step, if we have an abstract function and a concrete function, if the inputs are related by some relation, then after running these two functions, the output should also be related with some relation. We can make the specification more abstract by allowing non-determinism in them. So instead of saying we can only output a single result, we can use a non-deterministic monad, which is essentially a set, saying that, okay, we can have a set of allowable results. And to reestablish the refinement relation, we just say, okay, the concrete output is just one element of all the an element of the possible results in your specification. So we define this relation just to make it beautiful. We get this refinement statement, which is exactly the same as this one, just looks prettier. So that statement is what we prove in our functional correctness for each function. Okay, we've seen COGENT, we've seen refinement proof that are used in the COGENT framework. Now let's see, okay, how we extend the COGENT framework with property-based testing. If you look at the testing framework, it's actually is very similar to the verification framework, and that's intentional. So instead of an Isabelle functional specification, this time we have a Haskell executable specification, and the COGENT compiler, instead of generating an Isabelle shallow embedding of the COGENT program, this time we generate a shallow embedding in Haskell, which is a program that can run. So And also, like, the compiler generates a whole bunch of Haskell bindings so that this C code can be called from the Haskell code base. There are several things that we can test here. This error 1 can be tested with property-based testing. This error 2 can also be tested. So basically, instead of proving functional correctness, we can test functional correctness. So we have case studies of these two use cases in our paper. This error 3, technically, we can also test them using property-based testing, but that's not really something we're too concerned about because this part is covered by the automatic refinement proof. So unless we want to change the code generator or we want to do some engineering work in the compiler, we can use that as a way to ensure that the compiler is engineered correctly. But otherwise, we don't really care too much. So how do we relate the refinement proof and the property-based testing, and what kind of benefits do we get out of them? Traditionally, property-based testing, well, as the name suggests, tests properties, right? Just like the things that you have seen in the SLE example. But what are properties? Like, properties are just logical formulas, and the refinement statement is also a logical formula. So we can test that one with property-based testing. What we get is we can mirror the verification framework with the testing framework. Right. So like the Isabelle functional specification and Haskell executable specification are actually, they resemble each other very closely with some minor differences. In the Haskell executable specification, we also want to support some levels of non-determinism so that it can stay abstract. But at the same time, we need to know that it needs to run, and it needs to run fast, because every time like you run a property-based testing, it generates tens or thousands of tests. So you still want to keep them like the execution fast. For that reason, usually the degree of non-determinism or the degree of abstraction in the Haskell executable specification is a bit lower than the Isabelle counterpart. That's why it sits a bit lower than the other one. And if you want to use the traditional style of property-based testing, you can still do that. You just do that on top of the Haskell executable specification. So if you test your properties here, it's actually easier, and that's also something we do for the proof. We just prove high-level properties on top of the Isabelle functional specification. What benefits do we get? One thing is that you see, like full verification, formal verification is sort of a binary thing. If you don't have verification, or if your verification is not finished, you basically get no assurance. And on the other hand, like you have to fully verify everything to have high assurance. So you can see that in the middle, there's a big gap. Just to give you an idea of what's the time and effort required for establishing the functional correctness proof on top of COGENT semantics up to the Isabelle functional specification. In the BuildBFS, which is a file system that we implemented for verification, we specified the entire file system, and we formally proved the functional specification of two top-level functions, iget and sync. And you can see, like, for example, put them all together for 1,350 lines of COGENT code, we need to manually write about 13K lines of Isabelle proof, and that took 9.25 per month to finish. So this is still relatively expensive. So with testing, what we can have is that, if we don't have proof, or if the proofs haven't been finished, we use test temporarily. So we get some assurance. And we can have them all together, like mix up. some of them are tested, some of them are approved, so get better assurance. It basically builds this full continuum of different levels of assurances and different levels of effort, which enables this incremental approach to full verification. Sorry. And also, using tests in lieu of verification has its benefits. So, for example, testing usually requires a lower maintenance cost when your specification changes or when your program changes. Like, it's much easier to reestablish a test rather than a proof. And also, an extreme example is that when you optimize your program, the specification doesn't change, the functionality of your program doesn't change, but the proof may break because, like, you really need to know the internals of your implementation, and you need to find a different proof tree to reestablish your proof. But for test, there's no such problem. It's only concerned about the input and output. And also, even though like you have some magic wand, you can finish your proof in a second, it still takes time to check your proof. So as you're developing your programs, for example, for the iGet and sync functions, they together take 2 to 3 CPU hours. So depending on how many threads you run your proof, it can take tens of minutes to several hours. So which is a terribly long time for the development cycle. And with tests, it usually finishes within a few seconds, right? So it shortens the iteration. And also importantly, property-based testing provides good design guidelines to programmers, especially systems programmers, who are less exposed to the logic, to the formal stuff. So the COGENT language itself, as a purely functional language, is suitable for verification and also suitable for property-based testing because it doesn't have any hidden states. It only has like input and output. But COGENT programs, unfortunately, are not always the case. Depending on how you write the program, you can really get programs that are difficult to handle. And that difficulty in verification will be reflected in your proof exercise. So, but like when we say we want to design programs for verification, what are the criteria? And it's kind of hand-wavy. So basically, property-based testing can give you quick feedback, tell you like what is good design and what is good modularity that you should have in order to lend yourself to future verification. I don't think I have time to go through the example, but it doesn't matter. Just keep it. So yeah. So to conclude my talk, so we want to say testing, property-based testing, and formal verification, interactive theorem proving, they actually complement each other. And the novelty here in this work is that we use property-based testing to test the refinement relation rather than the traditional like logical formulas or logical properties. As a result, the test mirrors the proofs, and they can be used as a temporary replacement for unfinished proofs or proofs that you haven't started. And it brings us many benefits. It, of course, detects bugs in the programs and inconsistencies in your specification, and it reduces the effort in your formal verification because you see you get immediate feedback whether you have done something wrong. Also, it enables the gradual approach to full formal verification, and it serves as a guideline to developers. So there are more stuff in the paper, like it discusses lots of technical intricacies, like how we generate test data effectively, how we use mocks, and how we compose tests, and also like what kind of non-determinism and oracles we can use to make the testing framework more flexible. We provide case studies of the 2 errors that we showed in the previous figure, and we also shared our experiences and the lessons learned during this exercise. So thank you, and the project repository is here. Feel free to scan that QR code. It's not a scam. It's not an affiliated link, so feel free to. Thank you.
Thank you. Any questions? So the story that you're telling is similar to the quick chick story, where they use a property-based tester in Coq so they can test the lemmas rather than try to prove them. And one of the challenges they have in that system is that not everything is executable. If you have a inductive definition, you can't run it. You can only look at its definition. Only if you put things in the compute domain are you able to do that. So there's been a bunch of work to try to improve that. Does your situation change that? Or are there parts of your, I couldn't tell because I don't know COGENT and you didn't show any concrete examples. Do you have similar problems that only some things are executable, or is the structure of the system such that everything is executable, so it's very naturally testable?
Hi. If you're, so COGENT itself doesn't support recursion or iterations natively. So it doesn't really sorry, I'm not really sure what kind of problem you're referring to in the quick check framework.
What about? But we can let me add actually onto Mike's question, because I was wondering the same thing. So you showed the Corres predicate Zilin.
Yeah.
That state relation in that predicate, for instance, is that executable? I presume it must be, otherwise you wouldn't be able to.
Sorry, which one?
R. There was a big R in the Corres.
Oh, okay, yeah. Right. You mean the input relation or the output one?
I don't know, any of them, because I guess it all has to be executable, right? Otherwise you can't test it.
Not necessarily. So actually, we discussed that in the paper. For the input, ideally, we want them to be executable so that you can generate one from the other. You don't have to generate two independent outputs and try and hope that they correspond to each other, which really happens, right? So usually we want to define the Rx as a function, but for the output, it can be defined as a relation or just a function taking two outputs and returns a Boolean, telling you whether they relate or not. Does it answer the question?
I think it does in the affirmative. My actual question was, so I remember when Sydney was doing all of his refinement proofs, and you showed the example that he only covered a couple of the functions of the file system. I actually missed the beginning of your talk. I'm sorry if you covered this here already, but you mentioned this approach is useful for partial systems where you don't want to verify the whole system. So did you apply it to any other parts of Bilby to see how it worked, the file system?
Okay.
Yeah, I guess I missed the bit where you talked about your case studies. So yeah.
Mm-hmm. Yeah, so we actually covered a portion of the Bilby file system that wasn't formally verified. Yeah, we did.
Oh. Hey, let's thank the speaker again.
Thank you.